we're going to sketch a graph of, oh, let's go, y is less than 2x minus 5. When we're graphing inequalities, I'm going to start the same way that I would as if that had an equal sign there and just graph the line, which means for my class, I need to see 2 points on that line. I don't care which 2 points, as long as they satisfy the equation of the line. So I'm going to start with y equals 2x minus 5. And personally, I'm just going to find the x and y intercepts. So to find that y-intercept, I'm going to replace the x in the equation with a 0. So I'll have y is equal to 2 times 0 minus 5. So y is going to be equal to negative 5. And the coordinates of that y-intercept are 0, negative 5. Next, I'm going to find my x-intercept. I always find x-intercepts the same way, no matter whether it's a line or a parabola or something fancier we do in pre-calc. This is just going to be y equals 0. And then I'm solving for whatever the x value needs to be. So if I've got 0 is equal to 2x minus 5, and I'm trying to get that x by itself, I'm going to choose to add 5 to both sides and get an x value of 5 halves. So that means the coordinate is 5 halves, 0. Because when we list the coordinates, we're always putting the x value first and the y value second. Now, when we graph inequalities, kind of like when we were just doing graphing inequalities on a number line with numbers, and we had to pay attention to whether this has that or equal to bar or not, right? So when we're graphing on a number line and we've just got numbers, that or equal to bar means I've got a filled in circle, or we can use square brackets. If it's just an inequality without the underline bar, we would have that open circle or parentheses if we're graphing on a number line. When we're doing this on the coordinate plane, that equivalent of like an open circle means that we're going to put in a dashed line instead of a solid line. What that's going to look like, I've got my x-axis and my y-axis, and I'm going to put those coordinates on. So 5 halves, 0. I'm just going to label something as 5 halves, 0. And label this one as 0, negative 5. And then when I draw the line, I'm going to draw it in as a dashed line. And that's what indicates that we've got that strict inequality and it doesn't have the or equal to. Now, the next part, when I'm graphing an inequality, this says that I should be looking at all y values that are less than 2x minus 5. We've essentially split this plane into 2 pieces, kind of on either side of that line. And the way that we show this is we're going to fill in, we're going to like color in one side of this. There are different ways to figure out what side to shade in. I think the easiest way is to pick a test point and see if it makes the inequality true. So my test point, I'm going to choose 0, 0 as a test. So if I'm looking at y is less than 2x minus 5, just a little bit, then I'm going to test if I plug in 0 for y and I plug in 0 for x, is the inequality true? And I'm putting a little question mark there because I haven't decided yet. 2 times 0 is 0, 0 minus 5, I'm at -5. So if I look at 0 and -5, which one of those is further to the left on a number line? Right, which means -5 would be less than 0. So this inequality does not hold. It's not true. So I need to shade in the opposite side. Beginning of chapter 4 is all about monomials. And a monomial is any collection of numbers and variables that are multiplied together in a single piece. So here are some examples of monomials. Technically, just a number is a monomial. If I have a number times a variable, that's a monomial. If I had 9a squared times b to the 4th, that is also a monomial. If I had 7 minus 3x squared, this is not a monomial. The reason that's not a monomial is once I've got two pieces that are separated by either addition or subtraction, it's no longer a monomial. Now that vocabulary doesn't really matter, but this distinction does, because it changes everything that we're going to do. One of the reasons that it changes what we're doing is monomials are things glommed together that are all multiplied. So I just want to take a step back and talk about numbers for a second. We did this on the first day of class, but I had a bunch of people that added after the first day of class. So I want to roll back around to our additive law of exponents really quick. And say, if I have the notation 5 raised to the 3rd, that 5 is our base, that 3 is the exponent. And what that means is it's a shorthand for writing 5 times 5 times 5. This is the thing that mathematicians have decided on. And when they decided on that, all of our other rules about exponents follow from this one. So if I multiplied 5 to the 3rd times 5 squared, if I were to write those out in their other form, that would be 5 times 5 times 5 times 5 times 5, which means that I can recollect all of that together to say that's 5 of those 5s multiplied together. Or in terms of our additive law of exponents, that's 5 to the 3 plus 2. So if I'm multiplying two things with the same base, I get to add those exponents. If I had something like 5 to the 7th divided by 5 cubed, if I write out all of those individual 5s on top, I've got 5 times 5 times 5 times 5 times 5 times 5, 1, 2, 3, 4, 5, 6, 7. And on the bottom, I've got 5 times 5 times 5, which means I can collect these together to be a 1, and I can collect these together to be a 1, and these together to be a 1. And I am left with 4 of those 5s on top. Or as an exponent rule, I can get there by saying this is 5 to the 7 minus 3. So we did some practice with this just with numbers in that first chapter, and we're kind of ramping that up a notch in chapter 4. We're going to be working with all of those exponent rules, but now with monomials. So we're going to have letters and numbers all mixed up together. One of the things that is important, but I think we kind of take for granted, is that multiplication, we say it's commutative, and that means that the order that we multiply things in doesn't change the answer. Sometimes multiplying them in a particular order makes it easier for us to do it in our heads, but it doesn't change the outcome. So if I have 5 times 6 times 3, I can choose to multiply the 5 times 6 first, and then multiply that by 3. Or I can choose to multiply the 6 times 3 first. What is 6 times 3? Totally. I don't know that in my head, but it should be 90. I can also choose to reorder this and have 5 times and move the 3 in front of the 6 so that I multiply these two together first and then times 6. That one I can do in my head too. That's the easiest one for me to do in my head in terms of multiplying in that order. But when we say that multiplication is commutative, it means we can rearrange these in any order and we're going to get the same answer. Why I bring that up is when we're talking about monomials, if I have something like 3a to the 5th b squared times 9a squared b, I can choose to reorganize this so that my additive law of exponents is a little easier to pop out. So all of this is multiplication. If I don't put the dot between things, it is implied that it is multiplication. So that 9 is being multiplied by the a squared, which is being multiplied by the b. And to simplify this, I can rearrange and regroup. So I would regroup this to be 3 times 9, a to the 5th times a squared, and b squared times b. I mentioned this before, but for the sake of folks that added a little bit late, I only need to see the intermediate steps if you needed to do them. So if the instructions were to simplify and you went straight to a final answer, I'm totally fine with that. You could just write 27a to the 7th b cubed. If it helps you to write out the intermediate steps, then do whatever is going to help you to get the right answers. Split off the paper a little bit, but I'm going to flip the page. So I'm trying to give people a second to write. You need to write. Okay, a couple for you to practice. I encourage you to talk to the people around you to see if they're getting the same thing, or if you have questions, click on me as I'm walking around. How are we doing? It's a very quiet Friday. Don't worry. I'll talk for all of us. No, I really don't talk for all of us. It feels like, as I am walking around, that people are more comfortable with the first one than the second one. So let's go ahead and get these rolling. I'm going to do this in slow motion. Totally fine if you jump straight to an answer. I'm going to take a minute to rearrange these so that I've got 2 times 5 times x squared times x cubed, and then times y, so that my numbers get collected. My x's get to look collected. 2 plus 3 is going to give me a 5. Y is hanging out by itself. So my final answer would look like 10x to the 5th y. This one, I intentionally wrote it this way, but one of the things that is good to keep in mind is that that exponent just means that I'm multiplying the thing by itself. If I have x squared, it means I'm doing x times x. If I have 5 squared, it means I'm doing 5 times 5. If I've got some junk squared, it means I have the junk times itself. So this is the same as a to the 5th, b to the 4th, z to the -1 times a to the 5th, b to the 4th, z to the -1. And if I do the slow motion thing and I collect things together, I'll have a to the 5th times a to the 5th, and then b to the 4th times b to the 4th, and then z to the -1 times z to the -1. If I collect those a's together, I'm multiplying 2 things with the same base, so I add those exponents, and I end up with a to the 10th. Same thing with my b's. When I add those exponents, I end up with b to the 8th. And with my z's, -1 plus -1 is -2. So I am looking at a to the 10th, b to the 8th, z to the -2. I'm going to pause here for a second because there is kind of a distinction that I want to make about the way that I'm writing this answer. Most of the time, this is generally how we want to think about it for calculus. However, it's not usually the way that this is written as an answer in our textbook. And oftentimes we're going to have to go back and forth between this and its other form, even in a calculus context. So thinking back again to that first day when we were talking additive law of exponents and we worked through what negative exponents mean, this is equivalent to a to the 10th, b to the 8th divided by z squared. And this version is how we would write it if the question said something like, write your answer using only positive exponents. And there are going to be times where that's how we need to think about our answer. So it's important to be able to go back and forth between these equivalent forms. That's one of the overall goals that we're practicing in this class, is recognizing and moving back and forth between equivalent algebraic forms. If for no other reason than if you end up with some sort of multiple choice test in your future, it is important to be able to recognize different versions of the same correct answer. Good times? If we can do multiplication, we can also do division. So if I am moving into dividing some monomials, usually we're not using that little division symbol that you see in your calculator. We're almost always going to write this as a fraction when we're doing division with monomials or polynomials later. But so if I had 16 x squared y to the 4th z cubed divided by 4x y to the 7th z squared. There are lots of correct ways to get through this problem. I'm going to do a very similar thing to what I did on the previous one, where I'm going to group the things that kind of belong together and use our rules about each of those groups. Everything up here in the top is being multiplied, and everything on the bottom is being multiplied as well. So that means that I can regroup this to be 16 over 4, and then group my x pieces, group my y pieces, and group my z pieces. Even from here, we've got options for where to go next. I'm going to pick something, and if you don't like it, I'll show you another way. But 16 divided by 4, I can simplify that to be 4. And x squared over x, what's the secret exponent on that x?
1.
So, oh, I tried to draw one. So I have an option. I can think about those exponent rules, and I can think about that as x to the 2 minus 1. Or I can write out that x squared in the numerator as x times x and think about canceling an x over x. Totally up to you. I'm going to go exponent rules. So this is going to look like x to the 2 minus 1, y to the 4 minus 7, and z to the 3 minus 2. So my final answer here, 2 minus 1 is going to leave me an x to the 1. You're welcome to write the 1 if it helps you. Again, just be careful about your handwriting and that 1 not turning into something else if you're going to put it on there. I'm looking at y. 4 minus 7 would be y to the negative 3, and 3 minus 1 would be another z to the 1. So this answer would be totally fine, and it is equivalent to writing this as 4xz divided by y cubed. But this is the version that you would need if it says to use positive exponents. See people still writing, so I'm gonna give you a little bit more time. Okay. We talked a little bit about what makes something like terms so that we can combine like terms in a problem. But we haven't done super messy stuff and we don't need to do super messy stuff. But I do want to get some practice in with adding and subtracting monomials. I'm just going to write the instructions as combine like terms and simplify. So let's say I've got 5 minus 3x plus x cubed minus 4x squared plus 7x minus 15. Sure, I'll put there. That phrase, like terms, means that we're looking for monomials that have the same letters raised to the same powers. So if I look at this and I'm collecting those like terms, I know that my numbers I can group together. Again, I'm going to write this stuff out. You do not have to write this intermediate stuff if you don't want to. Just for this first one, I'm going to write it out so I can group. Oops. How about if I group the correct numbers together? So I can group the 5 minus 15. And then I've got 2 pieces that have x raised to that invisible 1. So I can group the negative 3x plus 7x. Then if I'm just going by increasing powers, I only have one term that has an x squared. And I only have one term that has an x cubed. So that's me like grouping the like terms together. And I'm going to simplify each of those. So 5 minus 15 is going to leave me with negative 10. Negative 3x plus 7x gives me a positive 4x. And then I have a minus 4x squared and a plus x cubed. The order that you write these in doesn't matter. But our mathematical standard is to either write them in this order or the reversed order, but essentially to keep your powers ascending or descending. And either one is fine. More typically, you'll see the powers written in descending order if you're like checking your work in the back of the book. But that guy's also fine. So now let's have some fun. Let's mix in some order of operations. So let's say I have 5 minus 3 times Should I give you all a minute to try this one? Or did you want to watch it? Okay, I saw some head nods. Let's do it. So I'll give you all a minute or two to try this one on your paper. Yes. Each thing, yeah, totally. Yeah. You're gonna want to 35 for you. So we're not gonna subtract first, just thinking about that order of operations. So multiplication is gonna happen before the subtraction, so you have to multiply it in first. Yeah. Back here.
Yeah.
Try to make it not too terrible, just messy enough that we've got to remember. Got to roll back to some PEMDAS. Does anyone want a little bit more time to keep messing with it on their own? No takers? Okay. So if I'm thinking about parentheses, then exponents, multiplication and division, and finally addition and subtraction, I'm first going to take a look at what's in the parentheses and say, okay, inside of the parentheses, is there any place that I can combine like terms? So if I look at this set of parentheses, I can't. Each of these are distinct monomials with different combinations of letters raised to powers. Same deal over here. I can't combine the 1 and the y. Exponents, well, I have things with exponents, but unless I know what the value of x is, there's nothing that I can simplify about that exponent. I have to just leave it as x squared. Same with that y squared. So now I'm moving to multiplication and division. Looking at this, I've got multiplication in a couple of places. I've got 3 times all of that stuff in parentheses, and I have x times all of that stuff in parentheses. I'm going to go ahead and distribute this 3 in. So I'll have 3 times x squared, and then 3 times xy, and then 3 times negative y squared. And we can decide if we want to take the minus sign with us right now or not. I'm going to go ahead and take it with us. So what I'm distributing in is that -3. So -3 times x squared, I'll have -3x squared. -3 times positive xy, -3xy. -3 times negative x squared, sorry, -3 times negative y squared would leave me with a positive 3y squared. And now I can take my x and distribute that x in. So if I'll have x times 1 and x times y. Plus x and plus xy. Now I'm looking to see if there is anything that has like terms in this. And again, like terms meaning that I've got the same letters raised to the same powers. And I think I just have one pair of things that have like terms, because both of these are in x times a y. So I am looking at 5 minus 3x squared. If I combine those two together, I'd have negative 2xy plus 3y squared plus x. And that's the best I can do in terms of being able to combine like terms. We've got a few minutes left, and I want to point out a couple of places where our brains often have a tendency to play tricks on us. So here's what I mean by that. And I'll just say things to watch out for. I wrote x minus 3. We're going to get to multiplying out polynomials. We're going to be talking about that on Monday. It is really easy if you are writing quickly or reading a problem quickly to see this as x minus 3 times x plus 5. Either because your addition sign starts to look like multiplication, or just because our brains do weird things. This, I can't combine anything in the parentheses. I can't combine anything in the parentheses. I don't have exponents. I don't have any multiplication. This just says x minus 3 plus another x plus a 5. And if I combine like terms, that's 2x plus 2. This one, I actually have to multiply all of the terms out. We'll talk more about this on Monday, but I'm just quickly going to do what the answer is, but these are not the same. And here I would end up with x squared plus 2x minus 15. Don't worry about that if that feels weird to you. Again, we're going to talk about that on Monday. The other thing that starts to sometimes, again, look the same would be if I had x minus 3 times x plus 5. Being careful about where you're putting parentheses in a problem really matters. So this, again, can start to look like we can imagine parentheses in there and see that as x minus 3 times x plus 5, but it's not. Again, here, if I were finishing that out, can't combine anything in the parentheses, so I would move on to multiplication. And if I distribute that out, I'd have x, and then distributing my minus 3, that'd be a negative 3x and a negative 15. Which would combine together to give me negative 2x minus 15. So even though these three things are fairly similar looking, where those parentheses are just like something to be careful about and be mindful about, especially as you're working through problems in this section. If you're copying a problem onto your paper, just be really careful that we're copying it down correctly.